Today, sixth graders, we're going to explore lesson 1.5, graphs of ratios. Just a reminder that we're working on or in our M2-T1 ratios tab. And we're going to find the one that says 1.5 graphs of ratios, they're growing. If you're working in your textbook, you're looking for page M2-69. That's where we're at. You can either work in your textbook or you can work right here in OneNote. Graphs of ratios. Okay, in this lesson, we're going to be plotting equivalent ratios on a coordinate plane. So we're going to be graphing them, and then we're going to read them from that graph. Let's get started. There's another word here we're going to explore here too. It says this one right here, linear relationship. Linear kind of sounds like line, and we're going to see the linear relationship of equivalent ratios on a graph. So let's keep doing. So far you've used scaling up, scaling down, tables, tape diagrams, pictures, double number lines to find equivalent ratios. How can you plot values on a coordinate plane to figure out equivalent ratios? All right, getting started. It says growing rectangles. Consider a rectangle with a short side of length 2, long side of length 3. In the first table, add the indicated numbers of units to both the long and short sides of the original rectangle. In the second table, multiply each of the original side lengths by the given value. For each rectangle, determine the ratio of the longest side. Okay, let's do one of these together in each one, and then I want you to finish this up. So the original says a 3, short side 2, long side 3. All right, this first one they want us to add. So if we add 3, or to the long side 3, we add 2 to it, it would be 5. And if we add 2 to the short side, which is 2, it would be 4. And the ratio would be 5 to 4. Down here in this particular table, you're multiplying. So if the original is 3 and you times it by 2, you'd get 6. If the original is 2 and you times it by 2, you'd get 4. And that would give you a ratio of 6 to 4. Go ahead and pause me for a second. Finish filling out this table. Okay, hopefully you had a chance to fill that out. We'll go back up here. If we're adding 3 each time, this one would be 6. If we add 4, that would be 7. And the short side, adding 2 would be 4. Adding 3 would be 5. Adding 4 would be 6. And our ratios would be 6 to 5 and 7 to 6. Down here, when we're multiplying, if we're going to times it by 3, we would get 9. Times it by 3, we'd get 6. Ratio of 9 to 6. And if we times it by 4, we'd get 12. Times it by 4, we'd get 8. Ratio of, 12 to 8. All right, so we were able to get our tables figured out. So let's consider these questions. What do you notice about the ratios for rectangles formed by adding to the sides of the rectangle? And question 2, what do you notice about ratios for rectangles formed by multiplying the sides? Make some observations. What do you notice about these ratios? And what do you notice about these ratios? Go ahead and just pause me and answer question 1 and 2 in written form and tell us what you observe. Okay, hopefully you had a chance to respond to those. The first one says, what do you notice about the ratios for rectangles formed by adding? Well, in every particular instance, the ratios, when we add, oh boy, that's a crazy looking thing there. Okay, when we add, I notice that the numerator and denominator, if we're going to write them like fractions, always differ by 1. Goodness sakes. Okay. I also noticed that the ratios were not I'm not sure why my iPad's freaking out, but it is a little bit. They were not equivalent. All right. What did you notice about the ones with the multiplying values? Well, I noticed that all of these ratios were equivalent. Sorry about my messy handwriting. I'm not sure what's going on with my iPad. Because we had ones like 3 to 2, 6 to 4, 9 to 6, and 12 to 8. And if I simplify all of them, they simplify down to 3 to 2. So I know that they are in fact equivalent. Not the case in the adding one. Let's move on. We're going to skip activity 5.1. So let's scroll through that. And I'd like you to get to 5.2, graphing equivalent ratios. Let's read this. It says, let's investigate how you can use a graph to determine other equivalent ratios and see how all the representations are connected. Stephanie runs a website for a local sports team that gets 50 views for every hour, 50 views an hour. The table shows the ratio of time to website views. So just taking a look at this table here, 50 views in 1 hour, that means she gets 100 views in 2 hours, 150 in 3 hours, and 200 in 4 hours. Okay. The double number line shown represents the same data. So we can do the same thing in a double number line. The top shows the views, the bottom shows the time, 50 views in 1 hour, 102, okay, 150 in 3, and 204. You could also represent it on a coordinate plane. So we could take each of these and treat them like plotted points, ordered pairs that we could put on our graph. All right, so let's see what that looks like. We've got 50 to 1 was the first one. So when we do that, we'd go 1 and 50, and we'd plot our point right there. 2 to 100, we'd plot that point. 3 hours, you get 150 views, and 4 hours, you get 200 views. It says label the remaining ratios on the graph. Well, what do we have left? I think we have them all on there, but let's keep going here. Let's go back up to our double number line. In 5 hours, she would have 250, and in 6 hours, she'd have 300, and in 7 hours, she would have, 350. I don't know why I wrote it like that. So let's plot those. At least let's plot those first two. So 250 in 5 hours. Go to 5 hours, and we'll go up here to 250, and we'll put a line. And in 6 hours, she would end up with 300. What do you notice? I want you to take just a second to ask yourself, what do you notice when we put these on a graph? What do you notice about all of these points? Say it out loud now if you can. Hopefully you said something about them seeming to form a line of sorts, okay? What this means and what this represents a linear relationship. That was that word we had on the other page. By plotting these equivalent ratios, because every single one of these ratios from this table here in the double number line are equivalent, because they're all equivalent, this forms a linear relationship. It forms a line that goes through the origin or through 0. It's a very special word that you phrase that you're going to have to use as you go on in algebra as well. And we'll come back to that. Let's keep going. So you have used lots of strategies to come up with equivalent ratios. Drawing pictures, tape diagrams, scaling up and down, ratio tables, double number lines, all kinds of strategies. We also can use graphs, and that's what we're practicing. Consider the question, how many views will Stephanie's website get in 6 hours? You know 4 different equivalent ratios from the original graph. The graph shows how to use the 2 ratios, 2 hours and 4 hours. We know 2 hours plus 4 hours equals 6 hours to come up with 300 views in 6 hours. So we're starting to see kind of a pattern there with our graph. Describe how to determine how many views Stephanie's website will have in 7 hours given each representation. So how many views will she have in 7 hours? All right, so how do we do that using the graph? Okay, well, in 7 hours, using the graph right up here, we probably can just kind of follow the line that we are making here. We can also look at 4 hours and 3 hours. 3 hours was 150, 4 hours was 200, so we could add those two together to get 350. So we can follow the line on the graph to make a determination. If we go back to using the table, if we go back here a second to using this table, how can we predict how many will it be in 7 hours? Again, we combine 4 hours and 3 hours, combine those together to know that it's going to be 350. We could also look at this 1 to 7, and we can times it by 7. So then we know that 50 times 7 will be 350. All right, so we can use the graph or use the table. Using the table, we can add the ratios for 3 hours and 4 hours to get 7 hours. All right, good. How could we use the double number line? So if we go back here to where a double number line is, again, we can keep filling in the hours as we went, 5 hours, 6 hours, 7 hours, and we can follow our pattern to come up with our double number line that way. We also, again, can use multiplication, use what we know about equivalent ratios to make a prediction as to what it can be. Let's just write C above. All right, good. One way to analyze the relationship between equivalent ratios displayed on a graph is to draw a line to connect the points. You can also extend the line to make predictions of other equivalent ratios. Sometimes all of the points on the line make sense. Other times when you draw a line, not all the points make sense. So it says draw a line through all the points that you plotted on your graph. And do they all make sense in this problem? Why or why not? All right, we already drew, well, we didn't really draw a line. Let's do that now. I'm going to pick my tool that allows me to draw. I don't think it's going to. I gotta be in my draw feature. If I draw it straight, it should snap into making it a nice straight line. It's not gonna work for me, but that's how we do that. All right, would all of these make sense is the question. 2 hours, 3 hours, 4 hours, anything in between, does that match the number of website views? Would that make sense? Go ahead and write down, yes, I do think it would make sense. Why or why not? All right, hopefully you came up with an idea that, yes, all values make sense because you can have fractions of time, meaning you can have a half hour or 3/4 of an hour. And so therefore, yes, we can have partial amount of views during that fractional amount of time. So yes, it most definitely makes sense. And the last question, how do all the representations, tables, let's list them here, tables, double number lines, and graphs, how do they all show equivalent ratios? How are they similar? Describe some of the advantages of each representation. So take a few minutes to jot down a few ideas. How can you look at a table and know that you have equivalent ratios or not? How can you look at a double number line, know if you have equivalent ratios or not? And how can you look at a graph and know if you have equivalent ratios or not? Go ahead and pause this video. Take some time to write something down for each one. Okay, hopefully you had a time to reflect just a little bit. Let's see. In a table, when I look at a table, how do I know if I have equivalent ratios? Well, all I have to know is that columns represent equivalent ratio. When I'm looking at a column, I'm looking up and down. So the top number is a ratio with the bottom number. And if that stays consistent, those are my equivalent ratios. With the double number line, I can make a dashed line. Oops. Connecting two parts to represent equivalent ratios. Let's look at what that looks like. So we see on a double number line, this dotted line represents the ratios that are equivalent that we're dealing with. And then I'm looking at a graph. If I'm to graph them all, how do I know if they're equivalent ratios? Well, I can see that each plotted point represents an equal ratio because it will make a straight line. And that goes through 0, right? So that's kind of my hint. Which one is easiest for you to see equivalent ratios? I don't know about you, but I kind of like the graph. It's very visual. You can see it right there. In the table, you have to figure it out a little bit. Maybe you like the double number line. It's really going to be up to each person which one they like the most. Okay, let's look at this last activity, 5.3, using ratio graphs to help us solve problems. All right, Augie burns 225 calories for every 30 minutes that he rides his bike. Complete the table to chart the number of calories burned for different amounts of time. Then plot them on the graph. Okay, here it gives us a chance to practice this a little bit. Let's first get the table figured out. We know that he burns 225 calories in 30 minutes. We have to figure out how many calories does he burn in 10 minutes. So I'm going to think my way through this. I think that I can scale down by dividing by 3, because 30 divided by 3 is 10. So I can do that on the top, divide by 3. And so I have to take 225 divided by 3. If I don't know how, I can do it off to the side. Goes in there 7 times, you get 21. 1 left over, bring down the 5. 3 goes into 15 5 times. All right, so 75. You can burn 75 calories in 10 minutes. To figure out 60, I could just double this, 30 times 2, and 225 times 2. Well, 225 and 225, oops, see, there's a brain fart for Mrs. Holiday. 225 and 225 gives you 450 in 60 minutes. And then I got to figure out 50 minutes. So a couple of different ways I might go about that. I think I'm going to go from 10 to 50, because I know that if I scale up and go from 10 to 50, I times by 5. So I can do that here, times by 5. So I have to take 75 times 5, and 7 times 5 is 35, plus 2 is 37. So 375 calories in 50 minutes. Okay, and they also would like us to plot these on the graph. So let's do that. Let's start with, first one listed here is 10 minutes, and we said 75 calories. So if this is 100, each one must be 25, 50, 75. So 75 must be right there for my 10. And then what do I have next? I can go with 30. 30 minutes, he can do 225. This must be my 225 mark. Come over to 30. It'll be right about there. Then I have 50. In 50 minutes, he can do 375. So this is my 375 mark. So I think I'll put my dot right about there. And in 60 minutes, he can do 450, which puts my point right about there. Okay, so it says, use your graph to answer the question. How many minutes would Augie have to bike to burn 150? Well, here's 150 right here. And let's see, that's the 150. And I'm going to try to use my graph to help me answer that. I think I'm going to figure out that he would have to, that dot's going to come right in along my line, my linear relationship. I think I'm going to see that he is going to have to bike for 20 minutes. And just to see if that for sure makes sense, if he can do 75 calories in 10 minutes, I want to know how many he can do in 20. I'm going to scale up by multiplying by 2, and 75 times 2 is in fact 150. So yes, that does make sense. How about B? How many calories can he burn if he bikes for 25 minutes? 25 minutes. Okay, well, couple of things I can do here. I can go back to my chart and I could see, well, he burns 375 calories in 50 minutes. So in 25, I know to go from 50 to 25, you scale down by dividing by 2. So I could take 375 divided by 2. And let's see. Get 1, bring down my 7. 2 goes into 17. How many times? 8 times. Then you get 16. Subtract. Bring down my 5. 2 goes into 15. 7 times. You get 14. Oh, I'm going to have to add a decimal. Bring down a 0. It goes in there 5. So it looks like he can burn 187.5 in 25 minutes. If you was going to try to use my graph here to help me figure that out, 25 minutes would be here. And so that's halfway in between those two, which should mean it should be halfway in between these two. So it should be roughly about there-ish, right? And that would be really kind of close to about 190 calories, I think. We'd have to move it up just a little bit to keep it on our line, which would make sense for our 187.5. So drawing a line can help us in coming up with our relationships. If we kind of put our line in here. Of course, it's a freehand line, so it's not exact, but we get the idea. How is the graph helpful? And were there any limitations when using the graph to come up with your values? Think about that for a second and write down your answer. Hopefully you said yes, it was good. It helped. Which one? I found it to be hard. It was hard to read some values. Like this one, right? 187.5. Kind of hard from this to come up with exactly 25 minutes. Where exactly does that lie? So we had to do a little rounding where the graph, or not the graph, the table helped us come up with a very specific answer. So sometimes the graph is helpful for a general kind of rule. Sometimes it can be a little trickier with some of them. All right, I think we'll stop there, sixth graders, and I will be giving you your assignment. You are to do that. That's right underneath this page.